And I think it's recording. Let's see. Yep, it's recording. Sweet. Okay. So here we go. Hey, Scott. Real quick, I need to survey you guys. Oh, I have a boot camp guy here because this is not me. I'm really nice. This boot camp is like really soft. It's really intense, but I'm a nice guy. Why are we starting with foods? Real quick, I need to know who I'm dealing with. I know I've met students. I know Scott. I've met you guys in the back. I know you guys. In terms of statistical savvy, general statistics, not SEM. If we were on a 1 out of like 10 scale, and 10's like, I'm the expert of the universe, and anything you say, I will question you. Or 1 is like, I got a C in statistics in my undergrad, which was me. I was engaged that semester, so it doesn't really count. So on a scale of 1 to 10, who here is below like a 3 in stats savvy? Oh, that's pretty, and now, okay. Below a 5? Below an 8? Above an 8? Oh, okay, good. I can say whatever I want. All right. I do want you to, if I say so, I'm not like super savvy on everything in statistics. It's a huge field. So if I say something and you're like, that's pretty close, feel free to correct me. I take correction. Let's see. Okay. One year I had a statistics professor attend. That was awkward. I was like, I watched everything I said very carefully. Luckily, he and I agreed, which was good. Made me feel good about myself. This is very important, which is why I start with it. You need to eat while you're here. We'll be going to the Cannon Center if you want to join me for lunch. I do have a question from remote folks. Chat says, statistics stuff from me. I'm probably still got a B. Huh. Good stuff. All right. I'm okay-ish, not too bad. Good. Okay. The Creamery on 9th is the best place for ice cream in the world. So we'll maybe walk there one day. If you want dinner at night, La Jolla Grove is good. Pita Pit's fun. It's just walking distance from here. You can Google all these. Bombay House has amazing Indian food. And Thai House cuisine is pretty decent. These slides are available in the Google Drive. Does everybody have access to that? It was in an email I sent out. There was a Google Drive link. The slides are all there. Today I'm looking at basics. That's the slides that I'm on. We talked about that. Oh, who here is interested in doing PLS on the 3rd day? Because usually it's like, all right, you and me, maybe in the back. Okay, we'll see what happens. Okay, we'll get to it for sure. But those who are totally not interested in PLS, you are welcome to skedaddle on Saturday whenever we finish the other stuff. You're welcome to skedaddle at any point. I mean, your time. Okay. Okay. Oh, this is me. So you know who you're dealing with. Yep. Oh, we have some remote folks who are interested in PLS.
You're gonna have fun in a few years.
I am. I have 4 daughters. Yeah. It's already pretty fun and intense. Yeah, they're aged 5 to 13. So it's just starting. Let's see. I've lived everywhere. This is my 31st home. I've lived all over the US, never lived in Kentucky, or Florida for that matter. Or New Hampshire, but I live in Boston. Close, yeah, it's pretty close. Similar accents, not totally, you know. Got my undergrad master's here at BYU in information systems, did my PhD at Case Western. Woo, we have 3 Case Westerns here. In information systems also. That's not me. That's Jake Dalton. He's an Olympian. But I'm a gymnast. I love doing gymnastics. I'm getting old though, I realized. It hurts really bad. I think I'm gonna switch to swimming. But I love gymnastics. It's fun stuff. Do lots of statistics, obviously, that's why you're here. My research, I do tons of research. I just had my 100th publication, 100th peer-reviewed publication. I'm super excited. It was last week, yeah. Woo! So that's good. I do a lot of research in augmented reality and human-computer, human-robot, human-AI interactions. I have a few companies around that idea. I have a dream analytics company. We just released version 4.1 yesterday, which is pretty fun. And I make video games because, oh, and I have a heart condition. Hopefully you won't see any of that. But I have to tell you, because like if I start clutching at my chest, not because you said something stupid, probably, it's probably because my heart's not beating properly. So I'll let you know if I'm having trouble, but that's just in case I need to set expectations.
Do you have chocolate in here?
Chocolate helps. I have some treats in my bag down there. So yeah, chocolate. I pretend chocolate helps. Chocolate doesn't actually help, but
Helps against dementors, they say.
it does help against dementors.
That was a similar reflection.
It probably is. Let's see. I'm looking at the chat. Anything else here? Whoop, whoop, whoop. Bye. All right, nothing critical. Okay. Also, remote folks, if you want to speak up, you're also welcome to. If you just want to put it in chat, you're welcome to. I see every time there's a chat, and so I'll go and check it every now and then. My standard disclaimer, stats is enormous. It's such a massive field, just like all of our fields. You can't know all of your field. It's impossible. I'm not actually a stats person. You saw all my degrees are in information systems. So my background's not even in stats, and I revealed I got a C in statistics. So, and the only reason I got through my graduate level statistics is because the guy sitting next to me was way smarter than me. So I learned statistics during my PhD and figured it out as I went along. But then made a bunch of videos and people used them, and I started learning more, and people ask me questions daily from around the world, and I have to learn stuff to respond to them. So I've accumulated a lot of knowledge around statistics, but it's mostly around SEM. That doesn't explain the picture. The picture is a golf course. I used to work on a golf course, and I used to aerate the fairway. And that little hole in the aeration hole is like, that's how much knowledge I have of statistics in general, whereas the whole golf course is the field of statistics. So I know SEM really well, like pretty good. And I know the software Amos and SPSS and Smart PLS pretty dang good. But if you ask me questions about R or another stats package or about some like general linear, whatever, multi-level, who knows what, I might have zero experience in that area. So I'm just setting expectations. I know one thing really good, and also SEM. Okay, let's see. So the plan, it's kind of intense. I'm literally going to cover 3 whole semesters worth of statistics in 3 days. That's the plan. And those of you who are going to move on to your doctorate, if they offer SEM, which they probably won't, which is weird because almost all social science fields require it for quantitative analysis, and yet nobody teaches it, which is one reason the YouTube videos worked out. But I'm going to teach you essentially 3 semesters worth of stats in 3 days. We'll start today with some stuff hopefully everybody's familiar with, and if I'm going way too slow, just give me some social cues. If I'm going way too fast, also give me some social cues, or just speak up, be like, I don't get it. But I'm literally gonna start with like error and p-values and confidence levels, just so we're all on the same page. But I'm gonna burn through that, like all of stats 100 level class in about half an hour, because I assume you're familiar with that. And then we'll slow down as we do more advanced stuff. Tomorrow, all factor analysis, and hopefully we'll get through all of CFA, which would be great. And if you don't know what that is, I'm glad you're here. We'll get to that, and then testing causal models on Saturday. Typically, the way the workshop rolls is we finish tomorrow's content a little early, and then either we just go home because we're all beat, or we plow through and do some of Saturday's stuff, so that Saturday we can just end before lunch if possible. I'm not gaming for that. I'm not aiming for that. But if it happens, it's historically that's what's happened. And then anyone who wants to stay after lunch, I sit with you. I help you with your dissertation or with whatever you're working on. And I'm happy to stay. You guys own me till like 5 o'clock, so I'm happy to stay till 5. the protocol for the workshop is mostly this is a demonstration. It's a doing workshop. It's not a like learning deep statistics and the algorithms and formulas and stuff behind it all. It's more like how do you use the tools and get what you need, and what does it mean? How do we interpret the results? And how do we prep our data and our models so that they work? So it's mostly a doing. I'm very happy to answer questions about the why and the theory and the stuff behind it, in as much as I have that knowledge, which isn't always the case, but with this stuff, I'm pretty confident. So feel free to ask those questions, but really this is a how-to workshop. Work with your own data. How many of you have your own data you plan to work on? All right, you guys in the make, oh good, cool. If not, I have data, it's in the folder, over here in the SEM Boot Camp folder, in the data folder. I'll be using it with you. And for those who, I also need to know who plans on like following along with the software click for click. Several of you. Okay, good. I want you to, but you don't have to for this workshop. You can literally just watch and hopefully glean something from what we're doing. Everything is being recorded, so you don't have to take copious notes. It's all going to be posted on YouTube, so you'll have access to it at that point. Stop me at any time. Any question, just stop me. We have a lot to cover, but we have time to answer questions. And feel free to help out others. Sometimes the software is not like super intuitive. Yeah, for those of you who've used Amos before, it's not super intuitive. So feel free to help each other out. If you've got it, help somebody else who's not got it. And if you don't got it, feel free to speak up and somebody will help you out. Let's see. Plan to use Smart PLS. Okay, so you'll hang out with me later. Good. All right. Any questions about protocol? Okay. Very important thing I forgot to tell you. The bathroom is over there, unless you're a man. And then the bathroom.
The ladies is also upstairs.
Is it also broken?
Yes.
Or not broken, they're fixing
well,
it?
being renovated, but upstairs works.
Oh, good. All right, so it's not on this floor. Go down a floor, up a floor. The stairs are right down the hall.
The down has been renovated already.
Oh, so it's nice.
Probably a better bathroom downstairs.
The up has definitely not been renovated.
Good to know. All right, go to the first floor. That's the best bathroom. We will occasionally take breaks just because it's burning hot in here and we're going to get exhausted mentally as well. And then we have a 2-hour lunch, intentionally a 2-hour lunch, so that you guys can catch up with whatever you need to do. So we can go to lunch. I can help individually, one-on-one, for anyone who wants to catch up or needs questions answered. And then at 5 o'clock or thereabouts, we're done. I'll stick around for a few minutes to help tie off loose ends, and then I'm gonna go see my daughters because this is the longest day I've ever worked in my life. I don't usually work more than 5 hours a day. So 8-hour days are exhausting. I don't know how people do it. Okay, and not a joke. Like really, how do people work 40 hours a week? That's exhausting. This is the hardest thing I do all year. All right, resources. The Stat Wiki is here. Most of you have probably seen that before. YouTube videos, the Google Drive folder. If you lost the link, here's the link here in the slides. I'll be putting everything. I've updated all the slides for the bootcamp. All the data is up to date. There's some remnants from previous years. Just filter around those. And Wi-Fi. Anyone not able to connect to the Wi-Fi? Good. Okay. All right. All right. Today, here's what we're going to cover.
Hey, can I ask you, James?
Yes.
So I kind of grew up through graduate school on SPSS, but I kind of feel some pressure at the water cooler when everybody else is talking about R and other things like that. Like they're cooler than I am.
They're not. They're not cooler than you.
So
Don't let them.
is there anything? So we're using SPS and Amos, which is what I've used as well, just because I grew up on this. There's some younger people here. Are people still starting off on SPSS and Amos, or is there kind of new things that are like these are for old people? And does that make sense? Yeah,
it makes sense. The question for the remote folks, we were wondering, are SPSS and Amos still cool and relevant, or should we even be moving to R and things like that? And the answer is, it depends on your field. Yeah. There's a lot of R in marketing and finance with deep data analytics and data mining and things like that. In more social sciences, like behaviorally focused and psychology focused, SPSS is still great. Amos is still great. Yeah. So we're good. We're still relevant, and people will still accept your manuscripts if you're using these tools. Yeah, good question. Whoops. So today we're going to cover briefly, very briefly, this stuff at the top. I'm assuming most of you know this stuff, or at least you've heard it before. And when I speak about it, you'll be like, oh yeah, I remember. Yeah, that all makes sense. And then we'll get more deeply into how to manage your data in order to prep it, because if you don't prep your data, it's useless when you start analyzing it. And then we'll get into the different types of significance testing. This is all just the morning stuff. And this is literally semester and a half of intro to statistics. And then in the afternoon we'll do EFA. Okay. If this stuff at the beginning is like snoozer for you, feel free to do email or whatever, Facebook, or I don't know, whatever the new thing is. I'm getting old and I don't know what the new thing is. Here's the data, or here's the model we'll sort of be basing a lot of our analyses on. It's just data I collected, let's see, 7 years ago. And it's about how people use Excel, which is not super fascinating, but it works pretty good for a boot camp for learning. We asked these participants, these Excel users, how playful they are with Excel, how much anxiety they have when they use Excel, their experience with it, if they think it's useful, to what extent this comprehensiveness of their use, do they use a lot of the features or not a lot of the features, and how's their information acquisition? Are they getting a lot of information in the results that they want, and how are the decisions they're making based on that information? Are they high quality, low quality? We also captured things like age, frequency of using Excel, gender, and also social desirability, which we'll talk about later. Anyway, so this is the basic model we're trying to build up to. Somebody asked a question. All right, it is a nice mediation model. Thank you. Okay. This is a typical SEM structure where you have independent variables on the left, mediators in the middle, dependent variables on the right, some moderation going on, some multi-grouping going on, some controls. This is very standard SEM. So this should help you with any SEM model you're building. Okay, we're going to jump right into it. I'm going to talk about, I have slides for everything, but I'm only going to use these as backup. I'm actually going to be in the software, talking through the software, and just doing it with you. And then we'll go back through the slides and make sure I didn't miss anything critical. Okay, so with that in mind, those who will be following along, go to the data folder and open up, it's called, let me zoom in here, it's called Bootcamp Original.sav. There are a bunch of boot camps ones, but get the Bootcamp Original.sav. If you're hungry, get the burgers. That one's fun. Okay, let's see, Bootcamp Original. Open that up and wait for SPSS to take forever to open. I swear it's gotten slower as my computer's gotten faster.
It was like the slowest software in the world.
Yeah,
I think my computer crashed. Even this morning I booted it.
Yeah.
Oh, did it crash here? It's like, oh no, it's just slow.
It's just really slow. It's like a massive Adobe product or Oracle product. Yeah, but it's IBM. So we'll wait. In my videos, you don't have to wait for this. I speed them up. While we're waiting for that to open, any questions, clarifications, comments? Can't find the Google Drive link. I will paste it right here. Let's see. It was in an email I sent out. Let me, really quick, I'm going to pause my screen, folks. So if you don't see my screen, don't freak out. I'm going to pause it so that the recording of my emails doesn't go on YouTube. Let's see, sent bootcamp. Here it is. Let's see, Google Drive. Stop doing that. There we go. Control-C. Oh, somebody pushed. Thank you. Thanks. Okay. And we'll increase that. All right, resume share. There we go. Okay. Hopefully your SPSS has opened. Anyone still waiting on SPSS? I'm using bootcamp.original.sav. All right. Who here has never used SPSS? Don't be shy. Yeah? Just a little bit? Okay, never? Okay, good. So I'm going to assume we're all novices for a moment, so we're all on the same page. Anyone still waiting to get SPSS open? We're good? Okay. Okay. So when you open up SPSS, when you open a file in SPSS, there might be a little window that pops up. Feel free to close that window without checking any options. And you'll see something like this. This is the data view. If you look down here, there you have a data view and variable view. I'm on the data view right now. Oh, nope, I was on the variable view. Here's the data view, where this is just your data. At the top, you see all your variable names. Like here's this anxiety 4. And then each row here is a participant in your data, where each cell is their answer to that survey question. So on this one that says adopt 3, person R004 said 2, which in this case was a somewhat disagree on a Likert scale. You have a bunch of menus up here, which we'll use. And then if you go down to the bottom, you'll see there's also the variable view. And this is where you can see all of your variables just stacked one on top of another, what type of variable they are, and what the survey question was that corresponds with that variable, and what type of variable it is. These should actually all be ordinal, but it's not going to make a big difference for our analysis today. So I should maybe talk about that real quickly. You have nominal, which would be grouped variables, variables like gender, marital status, industry, job type, things like that are just discrete types of groups. Ordinal, which some other software call categorical, ordered categorical. These are discrete values, but they do have an order from like strongly disagree to strongly agree. There is some numeric meaning to the number given, whereas with a nominal variable, there's no numeric meaning. If you have a 2 in marital status and I have a 1 in marital status, you don't have like more marital status than me. That doesn't make any sense. So the numbers are meaningless in nominal, whereas in ordinal, they are meaningful. And in scale, it's just a continuous value, like age or income. They have a continuous value. So that's what those are. Did I just change one I shouldn't have? Yes, I did. Whoops, that should be scale or ordinal, but that's fine. Okay, so that's what this is. That's SPSS. Let's do this. The first thing you want to do when you get your data is you want to scan it for missing rows that have a ton of missing data. There are different ways to do this. We could just sort of eyeball it real quick, scroll down, but we have a lot of data, so we might miss it, but I'll still do it. It looks like we don't have any rows that are too heavily empty, so that's not so bad. But just in case, what you could do is go to, I prefer using Excel for a lot of stuff. I'm just gonna hit Command A or Control A and copy this over to Excel to run a couple formulas on it. And over in Excel, Control New, paste that in there, just so I can see if there are rows that have a ton of missing data. One way you can do this is with this formula. Let me zoom in. Whee! Where do we go? Here we go. Equals count blanks, or count blank. That's a fun Excel formula. And what range? Well, just all of row A, or row 1. So here's the formula again, F2, count blank. For me, it's A1 to EA1. And what this will do is for any, it'll count however many cells have nothing in them. And that way you can see what percent are actually missing. For some of you, I'm gonna go like mind-numbingly slow, I'm sorry. Others I'm gonna go mind-blowingly fast. So roll with it. You'll be good. Here we go. So if you then fill that all the way down by double-clicking that little handle, we'll be able to see how many are missing how much. So just 1, 2, 1, 1. Not a lot missing. Is there anyone who's missing a ton? 1. Because often when you get your data, you do end up finding some that are missing like a lot, like the entire row is missing. We have a lot of 1s in here. But, oh, wait up, we do. Hey. There are a couple down at the very bottom, 379 and 380. Huh. Okay, they are missing the majority of, you can see where they cut off right here. They're missing the majority of their responses. So what we'll do is, the general rule, there are a couple rules you can follow actually. The general rule is if you're missing more than 20% of your responses, then you're useless. We can't use your row at all. Just delete that row. My rule is a little tighter. I like 10% because otherwise you start biasing the data. You start deleting if you don't handle those who are missing more than 10%. So I like to delete those who are missing more than 10%. Other people say if you have enough data, why not just delete anyone who's missing anything? Because removing a single or even 5 or even 10% of your respondents isn't going to bias your data. If you start removing more than about 10% of your respondents, there's a serious problem. You're going to start biasing your data, and you're going to wonder, well, why didn't these people answer my survey when the others did? So you can introduce some response bias there. So, but as long as we're not deleting more than 10% of our sample, we're probably okay. Other people say, well, you should impute, which means replace missing values with either known values or calculated values. I'll show you that in just a sec. Let's handle these two first though. Since we've removed all of our, or we've copied all of our data out of SPSS, we can do whatever we want with it right now and then just paste the whole thing back in there as long as we delete all the previous data. So let's do that. These two rows right here, I'm just gonna delete them. 379 and 380. Now, if you're working with your own data, you're gonna wanna keep track of what you're doing here. You're gonna wanna write down deleted 2 rows, 2 respondents due to more than 20% non-response.
Okay.
Yeah.
So you're actually deleting them.
Deleting, gone, yeah.
In SPSS, there's often an option which is exclude
Yeah.
values case-wise.
Yeah, list-wise or case-wise. Yeah.
Case-wise. Isn't this kind of equivalent? I mean, there, if there's any missing values, if you say
right, it'll exclude it.
It'll exclude it as well.
Yeah. And so what I'm doing is I'm prepping for when we're out of SPSS. So for SPSS, we could do that. We could exclude case-wise, and it would do essentially what I'm doing now, but it would exclude anyone who's missing anything. And what I'm doing is, but outside of SPSS, there's software like Amos that doesn't know how to handle case-wise missing. And so I'm prepping it for that. Yeah. I'm just gonna delete these 2 rows. Again, if you're doing this on your own data, you're gonna wanna write that down, deleted 2 rows, because they were missing more than 20% of their responses or something like that. We can also just sort this, since again, we have all of our data outside of SPSS. You wanna be careful if you've only copied some of your data, don't start sorting and deleting, because then when you paste back into SPSS, it's out of order and broken. But we've got it all. So let's go ahead and I'm gonna sort by this column, by this number missing. Sort largest to smallest. Whoa, what did I just, oh, I clicked on it, help. I gotta move this, move. There we go. All right, sort, largest to smallest. There we go. And we have those with the most missing at the top. It's not a lot, so let's just handle this in SPSS instead. Typically, if you're missing just a few values per case, you don't want to deal with it case-wise, you want to deal with it variable-wise, column-wise, because it's probably due to some particular variable. So let's do this. Let's copy all of our data in Excel, just copy all that and put it back in SPSS after we delete all the cases in SPSS. So make sure you delete all the SPSS ones because we deleted a couple and we resorted So I'm going to paste these back in. I guess I'm also pasting the blank counter. So we'll have a new variable. Hopefully it's pasting. Might be running slow for the paste. There it is. Might take a moment to paste it all with a lot of data. And we have a new variable over on the right called var001, which if you double click, you can rename it. I'm just going to rename mine blanks, or missing. That's a good one. Missing. Again, paste all your data over here after you've deleted all the data that was there. And then over on the far right, you'll see you have a new variable. And if you double click the column header, you can rename that variable to be, I named it missing. All right, for those following along, am I going too fast, too slow, just right? Too fast? Usually I'm too fast. It all makes sense in my head. So, all right. What we'll do is periodically, I'll save this data set to the Google Drive, and then you can use my updated data set if you weren't able to keep up. And I apologize, I do move kind of fast because I know where everything is and I know where to look at because I've used it for forever, but I forget sometimes. How do I get this data? Use the link above. There's a link right here. Click on that link. Lori, look above. Okay, here we go. All right, so now let's do this. Let's do a missing analysis. If we go to Analyze, and down towards the bottom, there's a missing value analysis. We can see what's missing values and what percent are missing. And this is by variable, not by case. So I'm just going to throw in all of them except ID. I don't need ID in there, and I don't need missing in there, obviously, because that's redundant. Get rid of that one.
What heading did you find that under?
That's under Analyze and Missing Value Analysis. There we go. And then I just stuck all the variables in there. I just clicked in here and hit Control A, and then put them all over there, but then put ID and missing back, because we don't need those. And don't worry about patterns or descriptives right now. Just use all the defaults and hit OK. And it'll think for a while. And then you have this, and it says, in order, what percent is missing from each one? Looks like we have nothing missing, nothing missing. Just a few missing here in EOU6. Sorry, this is small on the screen. I can zoom in. So just a few with missing. Oh, whoa, holy schneggies. This one has 46 missing. That's 12% of the data. That's probably too much to be useful. Let's scroll down any more. All right, well, that's the big one right there. Social desirability 7. Let's go find out what that one was. If we go to your variable view and you scroll to social desirability 7, you can see the wording on this one is, there have been occasions when I took advantage of someone. Yeah, I can see why people didn't answer that. There's a lot of missing on that one. And this is an interesting set of variables, the social desirability. I'll give you a preview of it now. It's whenever you ask questions on a survey, there is a socially desirable way to answer questions. There's a way that we think society would prefer us to answer. And so the answers we give are sometimes inflated or deflated. They're shifted, biased in some way by the social desirability perception. And so you can actually ask questions that are clearly biased towards social desirability. For example, I always admit when I make a mistake. Of course I do, right? I always practice what I preach. Of course I do. I never resent being asked to return a favor. Of course. Never been irked. That's a fun word. I like to gossip. There's clearly a right way to answer that question. And the extent to which we inflate or deflate our answers on these can then be used to control for that bias in others, in other answers. And so that's why we ask these questions. And we'll deal with those tomorrow. Anyway, we've learned social desirability 7 is pretty much useless to us. We're missing over 10% of our data on that. Over 10% of our respondents didn't answer that one. So I am literally just gonna delete it. It's too much.
It's also an indicator, though, not to go down
Yeah.
the rabbit hole, but the fact that 48 didn't, that's almost an answer in itself.
It is, it's
Right.
telling of,
Right.
yeah,
Like a score of 0 for social desirability.
it's not a useful question is what it's telling us because people won't answer it. Yeah, I just ran a study, I'm trying to still publish a study on bribery in Africa. That is a hard one to get straight answers on. People don't like telling you if they gave bribes, turns out. Yeah.
Could be the word taken advantage of,
Yeah, those are pretty strong words.
because it could mean.
Oh, people might not understand it. There might be some ambiguity there, and I took advantage. Yeah, you're right. Okay, there are many reasons why people might not answer your questions. Either they're sensitive, like this one is a sensitive question, or there's ambiguity in the question. They're like, I don't know how to answer that. Skip, I don't know. I was once asked in a survey if I enjoyed spending time with my children outside. And at the time, I didn't have children. And so like, how are you supposed to answer that question? Anyway, so lots of reasons they might not answer it. I'm just going to delete this row, this variable here. It does not want to respond. There we go. Clear. Just right-click the row number for that variable and hit clear. Okay, so it no longer appears in here. There were a few others that had missing values. I believe EOU6 was one of them. So if we want to go over to EOU6, if we go to the variable view, we can scroll up to it. It's all alphabetical right now, I believe. And you can find EOU6 and double-click it. Double-click the number next to it. And that'll take us to that column on the left. You can see we're missing 2 right here. Now, we're kind of getting ahead of ourselves, but there are many different types of variables, but 2 kinds I want to talk to you about, the way you can word variables and measure things. There's formative and reflective, and we'll talk more about that tomorrow or later today. But reflective means you ask a bunch of questions that are very similar in nature. They're all asking about the same thing. Formative asks about different dimensions of the same thing. And you might answer those questions differently, but for questions like EOU that are reflective, you're going to answer them all the same. As example, if I go back here and I read these EOUs, it's my interaction with Excel is clear and understandable. Interacting with Excel does not require a lot of mental effort. I find Excel to be trouble-free. I find it easy to use Excel to do what I want. Learning to operate Excel is easy for me. They're all saying the same thing. They're reflective. They're all capturing the exact same thing. And so you'd think the way I answer number 1 would be very similar to the way I answer number 2 and 3 and 4 as a rational human being. So if I go back and look at how this person who neglected to answer number 6 answered the others, I can probably guess what they would have answered for that one, or I could just average it. So you can say they answered 4, 2, 2, 4, 3, 3, 3. So averaging about a 3 in here. Is it evil, manipulative, and unethical for me to put a 3 in here? No. Here's why. Here's why. This one number, being an average of what they already responded, is first off a pretty good guess of what they would have put. An irrational person could answer this wildly, but a rational person must answer reflective questions similarly. So it's a pretty good guess as to what they would have answered. If these were formative, it would be unethical. I couldn't put that in. It's a wild guess, no clue. If it were categorical, like gender, I couldn't like guess the gender. But for a reflective perceptual question, for a single value, that single value, if I were to change this, even if I were to put like a 99 in here, this would not drastically change my results with 380 people. Putting in the average won't change a thing. It'll just allow me to proceed with my analysis. Yeah.
What if you didn't do that? What would
Yeah.
AIMS do?
Well, if I had missing values, most SEM software won't estimate. It says you need to deal with your missing values. It will not run. Yeah. So we need to deal with them.
It won't just delete that case.
No, it'll just say, sorry, you have missing values. You need to do something with them. Yeah.
Okay, that wasn't
Yeah. And so we have to do something with them. Yeah. And putting a 3 in there, again, it's a good guess. It won't change any of our results. It will only allow us to move forward. But what do you have to do? You have to report what you just did. You can't just go do that willy-nilly and then not report it. You got to say, one of our cases was missing, didn't respond to one reflective question in a set of questions. We averaged their response to all the other reflective questions within that set and stuck that in as a good guess. So that's what I'm doing. For this next person, it's 3, 3, 2, 2, 2, 3, 2, 2, 2. So about a 2, 3, somewhere in there. More 2s than 3s. I'm going to put the mode in there as a 2. Now there are other ways. Let's look at some other ways. We have a question on chat. All right. Yes, you would definitely report that you deleted the social desirability item. Let's see. Lori, did you end up finding the data set? It's called bootcamp original.sav. Hopefully, yes. Okay. Here we go. All right, let's go look at some of those other variables. Here's one, playful 4 is missing a couple values. Now, we can, as before, just guess. I mean, it's 2, 2, 2, 2, 2, or 3, 3, 3. I'm pretty sure we know what they would have put for those ones. So we could just enter those. In fact, that'd be the best route. But you could also go like this. You could go to transform up top, and then replace missing values. And then we're going to use a calculation to replace these rather than just punching in our own numbers. So replace missing values. Also, if you want justification from a paper for for putting in that number, like putting in the 3, you can look at Hare et al. 2010, the multivariate data analysis book. He says there are 3 different ways you can do known replacement values, which is what we just did, a known replacement value, calculated values, or deletion case-wise. So we use the known replacement value approach. If we go to playful 4,
Calculation would be
what we're going to do right now. Yeah. So playful, you could either do a mean, a median, or a regression-based calculation. For those who are doing the capstone right now, those in the back, our rule on missing data for this capstone is do not impute. Just delete the entire case. Okay. I'm going to stick playful 4 in here. And I'm going to replace with the median of nearby points. Median of nearby points. How many points nearby? We can just do the 3 around it. See, playful 1, 2, 3 to the left, 1, 2, 3 to the right. So would that be 6, I guess? Medium nearby points. Number of nearby points, let's just do 6. The 6 nearest points. And then you're going to click on the change button. And it's going to create a new variable called playful _4 _1. We'll hit OK. And so what that does is says it replaced 2 with a medium nearby points. And so if we go back to it, you'll see it hasn't replaced it here in this column. It's created a new. It didn't replace it. That's hilarious. Sort of. That was not expected. Let me try that again with a different approach. That's funny. That has never happened before. This is like my 9th boot camp, isn't it? That's never happened. Instead of nearby points 2, let's do all. And I'm going to hit OK. Let's see if that worked. It didn't replace it. What? I wonder if they changed the algorithm. That doesn't make any sense. Well, that's unfortunate. This has always worked in the past, so we're gonna just do it manually. Wow, that surprises me.
Welcome to my world.
Yeah, it's like only when I'm in front of people does it not work. No, it's always worked. Every boot camp I've ever done. Wow. Okay. Well, let's go back to Playful 6. Was it Playful 4? And we'll just put in. Obviously, this one's a 2. You can see right around them. It's all 2s. And down here, obviously, this one's a 3. Let's put that in there. Okay, you can see it's. And then remember, record what you do and report it. Okay. Were there any other missing? Let's find out real quick. A cool tool in SPSS is in the top left here. Right under the data menu, there's this thing called Recall Recently Used Dialogues. This will generate a list of all the things you've used most recently from most recent to least recent. So the most recent thing we did was replace missing values. That might be the only thing in your list right now, but you can just click on that instead of having to go back and find it through the menu system. You just click right here. And then it'll bring up missing values. Oh, we don't need to do that. What I need to do is do a missing value analysis, which is number 2 in here. A missing value analysis. And I'm just gonna check these again, just hit OK with all those defaults in there. And it'll show me which ones I'm still missing data on. Let's see. I can show you a trick. Check this out. If you double click a table, double click, you can edit it. Or you can even just right click any column and sort. It's in. Cool. And then when you hit close, the table back here has updated. Again, that was just double clicking the table. You can edit it directly. So we still have a few that are missing. Social desirability 3, 2, so 2, 3, and 4, and 10. Those are the only ones still missing. 2, 3, 4, and 10. So with those, I'm a little hesitant to replace those values because who knows what people would have answered on those, right? Oops. Back. Social desirability 2, 3, 4, and 10. You can right-click column heading and sort it from sort ascending, and that'll put the missing value at the top. You just sort ascending, and it sorts the whole data set. Yeah.
It says nearby points, but you don't get to specify which point. So if you have reflected factors with multiple indicators, is it going to jump to your next question?
I was hoping
when it's looking
right.
across that, or would you just drop some new variables with no data in there to push your?
Oh, that'd be a pain.
I'm just saying to push to push the next question over, so it doesn't pick up on that or copy paste out.
For remote folks, the question was when you do median of nearby points, what is the approach that SPSS takes to grab those nearby points? And the answer I would have given you last year when it worked was it just goes out from the center. It takes the one on the left and right, and outward. But this time it didn't work, so I have no idea.
So it worked for me.
Okay, maybe I have an old version or something.
Median versus mean.
Yeah, I did median.
Why?
Oh, because it's ordered categorical. They're discrete values, so there is no like point whatever 3.7. It's only integers. So I wouldn't want to use a mean because that would give me an unrealistic value.
Well, but aren't we kind of assuming, even though we have this, that these are all, kind of interval scale?
Yes, these are all interval scale, which is why I would use an integer for the replacement instead of, because if I use the mean, I could end up with something like 4.27, which isn't a real value on that scale. It doesn't exist on the scale that we use to record the data.
What if half of the nearby values were 2 and half were 3? Isn't interpolating and coming up with 2.5?
It probably would. It would have to pick one way or the other, is my guess.
But if you use mean though, so
If I did mean, yeah, I would have to average those.
That's not causing problems.
With 1 point, no, it's not going to cause any problems. Yeah, 1 point out of the 380 cases, nah, no issue. In fact, these are such small issues, it would be almost easier just to delete these rows. But here we go. Let's see if there is a way we can answer these consistently on these first 4, 5, which are positively skewed. This person put somewhat disagree on all of them. So I am comfortable putting a 2 in here. If I then sort ascending column, social desirability 3, whoo, they're missing a lot. There is no general consistency here, so I'm not very comfortable replacing that value. Same here, same here, same here. There's no consistency in these. So I would rather delete these variables, or these rows, respondents, than try to replace their values. Sort of. It's a sticky situation because I'm replacing 4 values out of however many thousands, 381 times however many variables I have. By deleting those rows, I'm losing their valid responses. Social desirability is only a control variable. It's not a critical variable in our data set. So should I delete all those valuable variables? I think not. I don't want to lose those valuable responses. So what I'll do instead,
Why did you decide to delete cases versus delete the variable?
I could delete the whole variable, but then I'm left with just 1, 2, 3, 4. That might work. But then I lose all of these valid responses. What I would rather do, what I'd rather do is do the thing that would have the least impact on my results, would least bias my data. And in this case, I would least bias my data by taking a series mean or median and just sticking it in there. So let's find out what that is. And you can see, I'll show you this later, but you can see, I'll just show you now, actually. This will be easier if I just show you. Check this out. There's this thing right here. And you may recall something like this from your Stats 100 class. When you have related variables, that could be plotted on an XY axis, and they have a generally consistent relationship. If for one of the variables I hold constant the X or the Y, let's say in this case I'm going to hold constant the X, watch what happens. So here's my data, here's generally its relationship. If I hold constant the X or the Y value, did I say I'm going to hold constant the X, sorry. And I put in a bunch of values that are just stacked on top of each other. You can see what it does to that relationship. It dilutes it a little bit. You can see the R square. You maybe didn't see this, but there is an R square associated with this, an R, and then you can square that. That dilutes, it decreases. And the slope of the line also dilutes. So there is an impact of just giving the series mean or median 2 values. But notice I only have 20 data points here. If I were to throw in 300 and then add 4 constant X values, it would have 0 impact. Almost, it would have a nominal, no different from 0 impact.
Is it true also that the mean, see, the ones you did are not the means to X?
Right. True. If I were to say
the mean, it's going to have even less.
You're right. Yeah, check this out. I was back here. Let me go like this, get rid of these. The mean for the X in this case is about 0. So if I were to add those points in on the axis here, keeps moving it, stop moving it. You can see that line's not even moving hardly. It's not changing the slope, it's just changing the intercept. So the relationship between them stays constant. So we're not damaging it too much. And that's my goal, do the least damage. So in this case, I'm just going to insert the series mean, which I'm guessing, well, let's not guess. Let's go to analyze, descriptives. Let's analyze.
Your missing data analysis table also has.
Oh, it has the mean in there? Let's just look at that. Thank you. Back here in the output, here's the mean right here. Sweet. So we were looking at social desirability, was it 3, I think? Yep, 3. And the mean for that one is 3.72. So if I want to use a real value, I would use 4. And I just insert that in there. And so that's what I'm going to do. And you just report that. Be very clear. Say we were missing 4 values on this variable. It was not possible to predict the value from nearby points. And so we just used the series median in this case.
So James,
Yeah.
and feel free to turn me off. But I do have an
You're good.
observation here. So if we replace it, so if you had a bunch of things, if you just relegated, you said, okay, I'm just going to do the means or the median.
Yeah.
Can you just go into the replacing missing values under transform and just say, just do it for all of them? Just
Yeah,
select
you
all,
can. You can do that.
select it, and you're done.
Yeah, you can do it for all of them simultaneously. Yeah. Let me show you how to do it for another variable. Maybe one do the remaining variables using that approach. Somebody remotely, let's see. Isn't there a positive social desirability and a negative social desirability? Yes, you are correct. So we couldn't use medium nearby points for social desirability scale because there's a positive and negative. Within social desirability 3, though, it's all positive. Okay. Let's do what Scott was mentioning. Let's go check out what still has missing. It would be social desirability 4 and 10. So what we could do is we could go to that replace missing values feature, and let's get rid of this play for. We already took care of that. But let's go down to social desirability. Was it 4 and 10? I believe 4, 4, and you can hold Control and click on social desirability 10, and then stick them both over here. What Scott was saying was maybe put them all in there, which we could. And what we're going to do is use the mean, the series mean for both of those. Looks like you have to select them one at a time. Series mean, change, and click on this one. Series mean, change, and then hit OK. And then if we go back, we can see all the way over on the right, those would have been fixed. If we sort it, we can make sure there are no, oops, sorted ascending, no missing values now. So that's how you do multiple simultaneously. Yeah, of course.
I don't know how to step out. So in the missing values table, sometimes you've got blanks over.
Yeah, like right here.
Extremes, even when there's nothing missing.
Yeah, let's see, that's for number of extremes, low and high. That means there's not enough variance on that variable to justify calling something extreme.
Okay.
Yeah. Yeah. I wonder why it's blank though. These say 0.
Well, that's what I was kind of confused about.
I wonder why that is.
0.
SPSS just broke in those cases.
Okay.
Isn't that comforting?
Yeah,
But sometimes it just doesn't work.
So it's just it's about not enough variance between.
That would be my guess, but then I would say just put 0 in there. But yeah, I don't know why it doesn't even estimate it. That's interesting. Huh. Okay. What we can do is there's a problem whenever we replace missing values. If you were to double click on the new variable, notice its label is this like S mean soch4, whereas what we want for real is the question. We don't want to lose that label. So the best thing we can do is just go copy the data from that column and go stick it back in the actual social desirability 4 column. Way over here.
If we, why don't we replace the existing variables?
So we could, if we replace the existing variable, it just deletes the label, deletes the question itself. Yeah, which is unfortunate. I wish you could specify don't delete or specify the label. So I just pasted that in there, even though it doesn't seem to have done anything. It should have. Let's find out if it actually did it. Nope, it didn't do it. Paste. There it is. Oh, Control Z. Because I pasted the wrong order. Ah! And now it's, there we go. Control Z. Okay, I'm just going to stick in the value itself. It was, for 4, it was 2.7, so 3, and for 10, it was also 3. Okay, 3, and sort this ascending, and put a 3 in there. Okay, and then you report all that. File, save as. This is Boot Camp original, no missing. Save this to our Google Drive folder so everybody will have access to that. So if you weren't able to keep up or do all the same steps as me, you now have access to that file once it updates in the folder here. Make sure my Google Drive updating is on. Updated just now. All right, that data set should be available. The new data set called Boot Camp Original, no missing. That's a lot of work for like a couple missing values. It actually goes way faster when you're not demonstrating and keeping people along. It'll take a few minutes.
And there's proper ways to annotate how to say exactly
What you did, yeah.
Okay.
There, essentially just be fully transparent. Say we deleted 5 cases due to a majority of missing data. We deleted, or we replaced missing values in 3 variables using the series mean or series median or median of nearby points or whatever you did. Just say what you did. Yeah, just be totally transparent and precise. And typically I do that in a footnote or in the appendix because nobody really cares. Yeah, they just assume you did it right. Yeah. Okay, that's missing data. Let me make sure I didn't miss anything from the slides here on missing data. Here we go. And we talked about that. Yep, talked about that. We didn't talk a ton about bias. We talked about people not responding. There's a problem with if you delete too many people, you got to wonder why they didn't respond and then what makes them different from those who did respond. So if you end up deleting all those who didn't respond on one question, you might introduce a sort of sample bias where your sample isn't representative of all groups within your population. A very common one is gender reporting. Turns out females report gender less than males do. That's how it works. And so if you were to delete all those who didn't report their gender, you would have very male biased data. And it's the same with income. A lot of people don't want to report income. If you delete those who don't report income, you only have those who did report income, which are different kind of people internally than those who do report their income or don't report their income. So be careful how you delete data because you could bias your data. We talked about this. We talked about this. We didn't talk about this. Best approach is just prevent missing data from the get-go. If you can prevent participants from not responding, that's great. Shorter surveys. You guys have all taken surveys. You ever take those ones that take like 20 minutes and after 2 minutes, you're like, oh, how long is this gonna take? Non-ambiguous questions. You ever take a survey where you're like, I have no clue how to answer this one. And if all the questions are gonna be like this, I'm done. Make it so that they're easy to understand. The way to do that is through pre-testing, which we don't even talk about in this boot camp. But there are ways to pre-test your surveys. Test them with other people to make sure that they know what you're asking. You could force completion on questions. This is tricky. You've probably been required to force, you've been forced to complete every response. Sometimes this is good because I get to the end of a survey page and I'm like, and it says, oh, you missed this one. I didn't realize I missed it. So I go and fill that out. But sometimes you're like, I don't want to answer it. And if you're forcing me to answer it, I'm done. I'm not going to answer anymore. So there's sort of trade-off to force completion. Bribing and motivating works really well with students and sometimes with other people. If you say we give out rewards for complete surveys, then that could help. Digital, this is obvious, but there are cases where you need to use a paper survey. I was doing a gerontology, is that how you pronounce it? Old people study. And they didn't want digital surveys. They wanted paper, so we gave them paper. But you tend to have more missing responses when you have paper. If you're concerned about your survey being too long, put your dependent variables at the very beginning of your survey, because those are the ones you really don't want people to be missing values on, and you don't want to estimate some calculated value. You want exact values for that dependent variable because that's the thing you're trying to predict. So stick that at the very beginning. Also put sensitive items at the very end. If your survey starts with, I like to gossip at times, people can be like, if this is how the whole survey is, I'm out of here. So don't start with like really sensitive stuff. Just put that at the very, very end. You ever notice gender, income, all the demographic variables are at the end of surveys? That's the reason. It's because some people find those questions sensitive and don't want to respond. So we got all of your other stuff, even if you quit when you got to demographics. Okay. Unengaged responses. We didn't talk about this. Let's go back to the data. Sometimes you get responses that are totally invalid, where people answer like 3 all the way across. That is useless. You recall back here, if I were to put 3s all the way across, it would mess with stuff a little bit. So we should examine that. Unfortunately, unless one of you knows, SPSS doesn't have a good tool for that. Anyone know otherwise? I haven't come across a good tool for that. So I've made up some hacks in Excel to look at this. If you copy your data, wait for it, and then go put your data back in Excel, delete all that. Here you go. There are ways to see if someone's not responding in an engaged manner. You could do this. Sorry, I'm probably going too fast. No, we're good. Okay, here we go. Equals. Let me zoom in a little bit. You could do something like equals standard deviation of this sample, and I want to see how they responded to all of my Likert scales, all my ordinal, which stop right around here at DO. So if I get all of the ones from, I'll show you my formula here. If I get all of the ones from, hello, F2, from B1 to DO1, it'll tell me the standard deviation of their responses. If they put 3 for everything, this number would be a 0. Just push that down. We can sort of scroll through it, see if we have any that are like not paying any attention. In fact, what we could do, which would be nice to make it a little faster, you could go to, while that's highlighted, go to the Home tab and then go to Conditional Formatting and just highlight cell rules if less than, let's make it less than 0.5, enter. Again, that was conditional formatting, highlight cell rules, less than, and I use 0.5 as the criteria. And so now we can just scroll down and look for a color. Scrolling. Looks like everybody was at least moderately engaged, or we have the wrong range in here. Let me make sure I got the right range. 1s to 5s. Oh, did I include 1? No, it's from B.
You started with B1.
I should do C1. Whoops. Gotta start with C1.
Why is that?
Because B isn't an ordinal. Yeah. C1, there we go. Enter. That'll make a difference. And now, fill that down. And is this important? Yes, this is important. Why? That guy answered 3s for everything.
Hope he didn't win the iPad.
Yeah, I would exclude that guy from the drawing. So this person, respondent number 134, didn't respond any different for anything. You could track the timestamps. You can see how long people took to take your survey and see if they finished it in 20 seconds or less than 2 minutes or something like that, and then delete them that way.
Some of your items are reverse scale, right?
All of these are positively scaled. I have no reverse scaled items.
seems like reverse scale would really be a red flag because
It would be.
if they're doing the items.
Oh,
that are
actually,
positive
I
scale,
do have my social desirability. The first 5 are positive and the last 5 are negative.
Yeah.
So I do. So this is truly weird.
Do you
Yeah.
ever give people heads up when you're actually designing a survey?
And tell them,
I'm going to examine how long it takes to do this in more scholarly terms.
so you could say that, but the problem is people will say, okay, I'll just leave each window open for a little longer. Yeah, I'll be looking for attention traps, things like that. So this person's a dud. Let's see if there are any other duds in here. Nope, just that one. So number 134, I believe it was. Let's go over here and look. 134, right here. 3's all the way across. So I'm just going to right click this person and hit clear. And in your report, your write-up, you say, we deleted 1 respondent due to unengaged responses. They answered 3 for everything. Just say that, and people know what you're talking about. All right, let's see. Someone's mute came off. Participants. All right, I'm going to mute you, unless you had something to ask. Everyone else's mute still on. Okay, cool. All right, so that's what you do with unengaged responses. There are actually other types of unengaged responses, not just beeliners like that. They might have put like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, something like that. Those are harder to catch. I look forward to the day when Qualtrics or whoever you're using comes up with a patterned response detection. That would be awesome.
But wouldn't it be, James, asking the same question or 2 points in the survey? One of them, I mean.
You could do that, yeah. You could ask the same question twice and see, except we might not be internally consistent. Yeah. For the you who works at Qualtrics? Here we go. Feature request.
Actually, no, it's a ways up, and that is.
All right, it's on the list.
Yeah.
Patterned responses. That'd be great. Thank you. Occasionally I make requests of software companies, and occasionally they listen. I made a request of Smart PLS and said, hey, we would love this feature. They responded immediately and made it. It was great. But they didn't name it the Gaskin feature. Yeah, I was a little sad, but it's okay. There are things called attention traps. There are various ways to word these, but if you put questions in there that clearly dictate a type of response, then you can go check to see how they answered those and then remove them if they answered them incorrectly. So I regularly eat car tires for breakfast. Most people, I don't know about Kentucky, but most people, right, would answer strongly disagree or somewhat disagree, I guess. Nobody's going to say strongly agree unless they're not paying any attention. So you can go check that one. Does anyone know of another good one? Another attention trap wording? There are a bunch. A bad one is, if you're paying attention, answer strongly agree. Because people know to look for that. They will do Control F or Command F and search for the word attention. And they will find it, they'll answer that one first, and then go back through and answer all the others. His experience with Mechanical Turk, Amazon Mechanical Turk. They'll just, yeah, they're in it for the money. Anyway, students too, in it for the iPad. I used to be one, it's all good. Yeah. Okay. Okay, that's missing data. Distributions, I'm not gonna spend a lot of time on this. You know what this is. It's a normal distribution with standard deviations listed down here, +1, +2, +3 standard deviations. If you are out here past 3 standard deviations, you're considered an outlier, an oddball. You might not be, what's the word, incorrect. You might just be an outlier. We'll look at that in a sec. The way to do this in SPSS is, it says here, analyze, explore in the histograms. I'm just gonna show you one. So let's do, if you go to analyze, descriptives, explore, analyze, descriptives, explore, and hit that. And then I'm gonna do it with a continuous variable because ordinal variables aren't that interesting, looking at histograms. But if we look at age, education, experience, let's do experience. And let's throw age in there as well. Just in the dependent list. And in the plots, choose histogram. The plots button here. That is really small. Choose histogram. It's one of the check boxes. Hit continue and hit OK. And it's going to run and it's going to generate these histograms for you. And lo and behold, we do have some oddballs in this data. We have a 9-year-old. That's not right. And so the data, I collected data from sophomores, freshmen, sophomore, juniors at BYU. So we would expect ages, on the very low end, 17. We have some 17-year-olds here at BYU. And on the high end, yeah, probably 26, 27 years old. And very occasionally older. We have some older students who return. So this 35, probably not an error, probably not a typo. This 9-year-old, probably a typo. We should go look at that. We go look at, here's the box plot. You can see anyone outside of these standard deviations or quartiles in this case might be considered outliers, but we'll look at that later. Here is experience. Looks like I had discrete values for this, so it's not as beautiful. We'll ignore that one. Let's go on to age though. There was an age outlier. If we go over to our data set, go find the gender variable, which I think is at the end. Here's gender right here. Not gender, age, my bad. Age. If you were to right click age and sort ascending, you'll get that 9-year-old at the very top. This is a highly unlikely value, especially given that this person has 3 years of experience with Excel. And let's see, where's education? Education, they have 1 year of college. If they have 1 year of college and they put a 9 here, what do you think the correct value is? 19. Yeah, at BYU, usually you start 18 years old, do a year, you're 19. This is clearly a typo. Are we allowed to just change it? Yeah, we are. And then we say, one person who had 1 year of college experience reported an age of 9 years old. We assumed this was 19. You just put that in your report.
So hypothetically speaking, I had a data set that had someone who said they were 41 years old but had years of experience.
Ooh, that's a problem.
So,
but how would you even guess what the right answer is there? Maybe they have 5 years of experience?
So my thinking was, I wanted to change the experience.
Yeah.
So I just took the average. I just took the whole average of everybody's experience. And we're talking 362
okay.
entries.
And what was the average?
The average was
it wasn't 50.
Yeah, it was like 15.
Oh, so hugely different.
Yes.
Okay. So in that one case, that is justified.
Okay, so
because they're clearly an outlier.
But the thing I didn't do was I actually did an average as opposed to a median. I probably should have done.
Well, since it's a continuous value, average is fine.
Oh, okay.
Yeah.
So
it's just with the ordinal scales, you want to use medians. Yeah.
Got it.
So it can be a real value.
So it was like 15.7, and I just rounded up. I think 16.
Perfect.
I stated that in my writing.
Yep, that's perfectly fine.
That makes sense.
Yeah. And changing that one value isn't going to damage, it's not going to bias your data. In fact, it'll fix any bias that was there from the outlier. Yeah. This is univariate outliers. There's something called a multivariate outlier. We'll talk about that a little later, maybe Saturday or Friday evening. Okay, do we need to check for outliers on all these ordinal scales? Not really. Well, I mean, what's an outlier on a 7-point or 5-point scale? If I put a 1, am I an outlier? It might be weird, but I'm not an outlier. Is my value erroneous? That's what we're really looking for, is erroneous responses. Like the 9-year-old, that was an erroneous response. It was incorrect. It was a typo. Can you have an erroneous response on a Likert scale? Not really. So we'll deal with Likert scale outliers when we look at multivariate outliers. I'm going to sit for a bit. Equilibrium's getting all funny. Okay. Make sure we don't have any questions here. We're doing good. Good. Okay. Here we go, back to here. We did that. We did that. Yep, we did that. Yeah, we did that. Skewness, you learned this in your Stats 100 class. Here's skewness. Do I remember which one's a positive right or left skew? Nope, I don't remember. It's like type 1 and type 2 errors. Who keeps track of those things? You can Google it. I don't know. And if I don't know, then you don't need to know unless you're taking a test. I get by just fine without having to, I mean, you got to delete something, right? You can't remember everything. Most people can't remember everything. So there it is. That's skewness. What's the problem with skewness in SEM? SEM is largely regression based. Anytime you have a regression-based analysis, you want fairly normal distributions or else your outcomes are biased. They get pushed one way or another, and you get what are called untrue estimates. Let's see, Dr. G, can you email me again the Google Drive link? It's just above. The Google Drive link is just linked above. Can someone else just repaste that in here? Thanks. Yeah, anytime you have skewed data, if it's strikingly skewed, like a lot, it can bias your results. So you don't want like severely skewed data. There are different tests for that. There's a link. Thanks, Carl. There are some tests for that. There's some really severe tests, and there's some more rational tests. We'll look at both. And we'll do that right after we look at this. There's also something called kurtosis, which is a fun word to try to fit into conversation. If you're looking for fun ways to entertain yourself. You have kurtote, which means not enough variance. It's really tight, everybody answered the same. In fact, we have some kurtosis in our data set. When it comes to age, it is a really tight distribution because we were just surveying sophomores, freshmen, juniors at BYU. They're all like 18 to 22. So there's some expected kurtosis there. You don't want too much kurtosis or else there's not enough variance. And in regression-based statistics, you need variance to predict something. If something doesn't vary, you can't predict its variance, if that makes sense. So it has to vary to predict its variance. Yeah.
That's one reason why we're moving away from single source data sources these days in scholarly writing, because the propensity for kurtosis.
The question for the remote folks who couldn't hear, the question is kurtosis or propensity for kurtosis one of the reasons we're moving away from single source data in rigorous publications in academia? The answer is no. Kurtosis isn't typically a terrible issue in social sciences, unless you're asking really socially desirable type questions like, do you lie to people? Everyone's going to answer no. I actually got this data back. We were sampling parents, and we asked them on a scale of, dumb as a rock and smart as Einstein, how smart their kids were. The kurtosis on that thing was ridiculous. Everyone said Einstein, all of them, except like some bad parent. I can't remember who, but everyone thought their kids were way above average intelligence. Anyway, but no, that's not why we're moving to single source or multi-source. That's for other reasons, which we should talk about at some point. Window. I arrived late from Florida State. Mixed up start time. Yes, this will be recorded and posted, Lynette. It will all be posted on YouTube. No worries. Even your question here. Okay. Let's go ahead and look at this in SPSS. So if we go to SPSS, go to Analyze, Descriptives, and Frequencies, I believe is the best approach. Again, that was Analyze, Descriptives, Frequencies. Let me just make sure this is the right one. If I click on Statistics, yeah, this is the right one. If you click on the Statistics button, check the box for skewness and kurtosis, and hit Continue, and then just stick all your variables in there. Control A, except we don't need ID in there, obviously. What about categorical variables like child order? Do we want skewness and kurtosis on those? The answer is actually it'll be handy to look at. Because what if there's no variance in our gender, for example? We have all female or all male data. Well, we'd want to know that. So stick all those over. The only ones I didn't throw over there were, oops, there's ID, let's put that back. ID missing, and then these 2 extras, which I should just delete from my data set because I already replaced those values. Anyway, and then again, make sure you, in the statistics button, you've clicked skewness and kurtosis, continue, and hit OK. And it's going to produce a whole heap of stuff. I'm just going to scroll up on the left here and jump to the top of it. Produces this table, which is pretty handy, but organized horizontally, which is unfortunate. I wonder if you can do this. View, pivot, transpose rows and columns. Ha! Hey, look at that. I just learned something new. I learn something new every year doing this workshop. Stuff occurs to me and I think, I wonder if you can do it that way. Hey, that's way better. Yeah, double click it, and in the pivot, you can transpose rows and columns. That's slick.
You double click edit content.
And then, yeah, go to pivot and rows and columns.
Okay, James.
Huh?
That's been causing me some questions here.
Yeah.
Yours are showing up as variable names. On mine,
Oh.
they're showing up as descriptive.
Who else is having that issue? Oh, that's a pain in the rear. Oh, I'm so sorry. And remote folks, some of you aren't seeing variable names here. You're seeing variable labels. Oh, that's terrible. Let's fix that. That's so bad. Go to up here. Go to Edit, Options. If yours look like mine, don't worry about this. Don't do this. But if yours look ugly like this, do this. So yeah, Edit, Options, and then in the Options in the General tab, in Variable Lists, change this one to Display Names. But there's more, so don't hit OK yet. And then over here in Output, the Output tab, change this bottom one. Instead of, I think the default is values and labels or something like that, just choose labels. And the top one, make sure it's just names, not names and labels. And same with the one below here, pivot table labeling. Should be names on the top, labels on the bottom. And then hit OK. And then it's going to say, hey, I'm going to reset everything. So it resets everything. And then you have to rerun your analysis. But when you rerun it, again, that was frequencies, analyze descriptives frequencies. Notice you'll have variable names here instead of labels. It used to look like this, which is awful. So now it'll look like this, which is kind of nice. And your output will look way better too. Did that fix it? Oh, good. Okay. Did that fix it for you, Scott?
Just a second. I'm about to read.
Okay.
Oh, it reset my dialog box.
Yep, it's going to reset all dialogues.
Yeah, so far so good.
Woohoo! Yay. Okay. Once we look at this, we're going to take a 5-minute break. I need to up my blood sugar. My heart keeps skipping. But let's, once you run that analysis, again, go to the top and look at that table, which for you, if it's horizontal, again, you can just double click it and go to pivot and transpose. What we're looking for in here is in the skewness column and the kurtosis column. We're looking for values that are kind of extreme, greater than the absolute value greater than 3. So we look at skewness and we scroll down. Oh, we can sort it. Double click, right click, and sort. Descending. And notice we have education is the highest skewness. Not a big deal. It's not above 3. 3 is sort of our cutoff.
I thought the standard was 1.
So there are many different published thresholds. The most strict is like the skewness divided by its standard error has got to be greater than 3 or something like that. Then there's 1. Absolute value's got to be less than 1. And then there's another one, it's got to be less than 3. Another one's 3.3. Another one's 10, actually. Yeah, 10 is a huge one. I think 10's a little extreme. In practice, I've done heaps and heaps of these studies of students. In practice, anything above about 4 starts to bias your data. But that's not published anywhere, so don't use that one. 3.3 is published. I think I have it on the slides. Let me check it. Here we go. Sposito gives us plus or minus 2.2, and Klein gives us 10. So if you're having trouble, that's the beauty of stats and science. Just pick the threshold that you want and cite that article. It's not cool, but it's cool. The goal of the SEM process is don't bias your data. You don't want to end up with false negatives or false positives by accident or on purpose. So check with and without changing things and see if it makes a difference. Okay, but in our case, that's less than 2.2, that education, so that's not a problem. Let's look at kurtosis, sort, and the thresholds are the same for kurtosis. Descending, holy cow, 17. Oh, education. Again, I was sampling mostly sophomores, and then there were a couple freshmen and a couple juniors. So this doesn't surprise me, but now I know that there's an issue. So if I were to use education as a predictor or as a predicted variable, I wouldn't expect much effect. It's going to be hard to predict or hard to use as a predictor because it just doesn't vary. So if we don't end up with good results on education, now we know why.
So if you say similar standards, then is height would be 1 standard deviation, or a value 1. Looser would be
3, and then 10 is like you're trying to get away with something.
Yeah.
How do you write that up? Just say, based on the published threshold of X, whatever it is, cite, we had no kurtosis issues except 1 variable, education. Actually, 2 variables, education and age, which for our sample is completely rational because they're students in the sophomore year.
So one of the things you've talked about in videos is the double or tripling standard error.
Yeah.
In comparison to the number of.
That is a super strict approach, but that is a way to do it. Yeah.
Plug in for that yet?
I don't have a plugin for that. You have to just paste this in Excel and do the division yourself. Yeah. 2 extra steps.
Right.
We do have a couple other issues. You see system satisfaction 3 that's kind of high. It's not alarming me. What I would report in my write-up is system satisfaction 3, and maybe I'd give the wording, and also design expectations fit 4, and I'd give the wording for that. We're above 3.3, but only just, and I'd give the values for them. And I'd say we weren't terribly concerned. These aren't extreme values, but they are high. We opted to retain these variables in order to retain the integrity of the scale. And because they weren't too extreme, they're not going to compromise the integrity of the statistics. You could also, if you want to do a robustness check, you could try it with and without those 2 variables and see if there's any difference. And if there isn't, you can also say that. Okay. Cool. What can you do anyway? I mean, about skewness on an ordinal scale. On an ordinal scale, you can't transform it because it's discrete values. So you can't transform, so you can't do anything to make it more normal. You can only say, it was not normal, therefore we did this, which is not use the variable or use the variable. On something like age that is more continuous, we could transform it. And the best video for that on the internet is this one. Do I list it here? I don't. Dang, I should list it here. I'll put it in the notes. I'll change it right now. The best video is by my buddy, YouTube, 2-step normalization Templeton. Here it is, 2-step transformation, Gary Templeton. Let me just share this. I'll add it to our slides. Copy. There we go. And put it in the slides right here. Need to transform continuous variables. There you go. Continuous. Okay. Nobody has that. Good. So you can do that if you want to transform. There's often not much transformation when we're doing SEM and social sciences because we often use Likert scales instead of continuous scales. Okay, that is saved. Let's take a 5-minute break and come back to this. Remote folks, make sure I hit record again when we return. Otherwise, it won't record. So I'm going to pause recording. All right, resuming recording again. Let's see. Good. Okay. Here we go. We didn't finish the normality. My blood sugar was all wonky, so thanks for putting up with me. There is below this in your output. Let's see if it's actually is it below at the very bottom? Oh, where'd it go? Maybe I didn't include it because I don't like it. There's a test called a KS test or the SW test, the Kolmogorov-Smirnov or the other one. Also never going to be tested on it. Huh? Shapiro-Wilk, that's the other one, Shapiro-Wilk test. These two tests are tests of normality, and they are exceptionally strict, like crazy strict. Something that has a skewness value of 0.7 might be considered non-normal according to these tests. I've never, not once in my 100 publications, reported the KS or SW test, ever. And I've never been called on it. So I've always reported the skewness or kurtosis values as my criteria for normality, and it's always been bought. And even at the most rigorous journals, at the top tier journals, they don't call me on the Shapiro-Wilk or KS test. Kolmogorov or whatever it's called. So if they call you on it, I have seen the KS test used before for non-response bias. Yes, that is another thing you can do. Although I usually use the Levine's test for non-response bias. So hopefully they won't call you on it because it's a super strict criteria. And if you use the KS or SW test to filter out cases or variables, I guess variables in this case, that are too skewed or kurtote, then you're going to be filtering out too many variables. It's going to ruin your data. So I wouldn't use those tests. Okay. In fact, I don't think I even put them on this slide. And that's it for the basic statistics. That was way more than an hour. Yeah. I do actually look at the QQ sometimes. The QQ over here, let's see, analyze, descriptives. Oh, it's explore, I think. Explore, yeah. And I'll just do these two for now. But you can do a QQ test. It's not, is it normality plot, I believe? Normality plots with the test. Hit continue, hit OK. Just watch, don't follow along on this one. And it'll produce these QQ plots. Normal is on the line. Non-normal is off the line. And you can see we do have some non-normalness according to the QQ plot. And you can report those and show how far off or along the line they are as a good indicator of your normality. The QQ test, it's this one that's produced when you do analyze, descriptives, explore. Oh, what does it mean?
Yeah, what does it mean?
Does anyone know what QQ stands for? I have no idea.
Oh,
I have no
just
idea.
look at the line.
Yeah, you just look at the line.
Okay.
And in the dots should be close to the line. If they're not close to the line, that means it's not normal.
I'm gonna write that. The dots were close to the line, so it was good.
Totally legit. I've never reported a QQ plot, ever. But they exist, and maybe some journals require it. Now you know they exist. So there's that. Okay. Testing for significance. This is critical. Hopefully most of you understand this, but I get a lot of questions quite often about how SEM didn't work for my data and why isn't it working? Why aren't these estimates significant or whatever? And it's because they're trying to answer a research question with SEM that should have been answered with ANOVA or t-test or something like that. So you should know which ones should be used at what times and for which types of hypotheses, and don't mix them up. Often you can get what you want with a simple t-test. You don't need complex SEM. So know what you need. The difference is you have two main types of hypothesis tests. There are actually several others that I'm not going to cover, like growth modeling, survival analysis, cluster theorizing, measurement theories. But anyway, there are two that I want to talk about, which would be difference of means and variables moving together. Difference of means is you have these two populations and they have different averages on some variable. You can use a t-test to do it for two groups, ANOVA to do it for more than two groups. A typical hypothesis here would be something like Australians live longer than Canadians. That should not be answered with SEM. That should be answered with a t-test. Whereas variables moving together, that means when one varies in to one extent, the other varies also with it. And the variance in one can predict the variance in the other. So as, for example, as autonomy increases, so does job satisfaction. As autonomy decreases, so does job satisfaction. And then, of course, correlation doesn't imply causation, whereas regression actually implies causation, but doesn't dictate causation. Just because you show in a regression there's a significant relationship doesn't mean you have a causal relationship. It just means the regression worked out. Cause is established theoretically, not statistically. The null hypothesis, also critical. Most of you should learn this in Stats 100. It's the thing where there's no effect. Don't theorize that. I see that quite often as well in emails to me from doctoral students. One or more of their hypotheses in their dissertation is there is no effect. There's no relationship between this variable and that variable. So why the heck are you doing your dissertation? I mean, like, if you're predicting there's nothing going on, that's fascinating. I mean, unless all of research to that point shows that there is something going on, then it makes sense to theorize the null hypothesis. But otherwise, it makes no sense to theorize the null hypothesis. So don't do that. But you need to know what that is, because the p-value is all about the null hypothesis. Your p-value is the probability that the null is correct, right? That there is nothing going on, which is why a p-value of 0.05, 5% chance there's nothing going on is what we use. It's 5% chance the null hypothesis is actually correct. Anyway, so that's null hypothesis. Looking at those difference of means tests, they're good to show via distributions, histograms. In this case, the test for age at death. Here's Canadians, here's Australians. This is totally bogus data. I made this up. Don't write reports on this. Canadian, the average is somewhere here in the middle of the distribution. Australian, somewhere here in the middle of their distribution. The question we're trying to ask with this ANOVA, or t-test in this case, because just two groups, is are these means, is the difference between these means different from zero? Or is the difference between the means actually no different from zero? If they're no different from zero, then we can't say that these distributions are different. We can't say that the hypothesis is supported. There is no difference in age at death. But in this case, we're probably pretty confident there is a difference in means because they're fairly widely separated and their distributions don't fully overlap. But a t-test would give us a p-value for that. And we can go look at that right now. So with ANOVA, if we go to our data, here's our data. And we want to do a t-test. You go to Analyze, Compare Means. Whoop. Let's do an independent samples t-test. There are a bunch of different t-tests for different things. Here's the independent samples t-test. And we'll say, go to the very bottom here. I have a few variables we could use, like enjoyment, usefulness, decision quality. Let's look at decision quality. Throw that in as a test variable. And we want to know, does decision quality vary based on, let's see, we have some grouping variables here. We have gender, we have child order. I think child order is like 4 or 5 different categories, so we'll have to use gender here. I'm going to get in trouble. Let's not use decision quality. Let's use enjoyment. Because I don't know what the answer is. You know, let's just have some fun and throw all three of these in there. Okay. And then let's use gender as the grouping variable. This is actual data. I didn't make this stuff up. This is actual respondents. In a t-test, you need to define the groups. So click on Define Groups. Group 1 in our case is 1, I believe. And group 2 would be 2. I better double check that. You can see over here in gender, it is 1s and 2s, not 0s and 1s. Okay, so groups 1 and 2. Options, I want a means plot. That's for a different thing. Hit OK. And you get the t-test. It gives you the means for male and female. And then down here in the t-test table, it'll show you the p-value for the difference between those two distributions. Or, well, between the two averages. And we are looking for p's, sig values less than 0.05 for the most part. And so it looks here that there is no difference when it comes to enjoyment, when it comes to decision quality, when it comes to whatever the other one was. There's no difference between men and women in this sample. Let's do this though. Let's do an ANOVA. Analyze. Compare means. One-way ANOVA. And this allows us to compare multiple beyond 2 groups, 3, 4, 5 groups, however many groups we have. And so I'm going to go to the bottom again, and I'm going to choose child order as my factoring variable. So that's the grouping variable. And what this will do is I don't have to define the groups, it just takes all the groups and looks at their differences. And let's throw those same 3 variables in here: enjoyment, usefulness, decision quality. And I want to look at a couple things. I want to see in my post hoc, you'll see there are a bunch of different options for post hoc pairwise comparisons, where it'll compare every group to every other group. Which one you pick doesn't make a huge difference. They're just doing pairwise comparisons. I like Bonferroni, other people like Tukey. Pick which one you want. They come up with the exact same results. I don't know why there are all those options. I'm sure there's some assumptions that I'm failing to consider. In the options, click on means plot. This is really handy. And hit continue and OK. And what this will do is it'll produce a few things. Your ANOVA will say, is there a difference across all groups when it comes to enjoyment, usefulness, and decision quality when using Excel? The answer is yeah, look at that p-value. Holy cow. This p-value means that the probability that the null hypothesis is correct is like 0%. There's definitely something going on. There is an effect. We can go down to our multiple comparisons table. Actually, let's skip that table for now. We'll come back. Go to the plots, the means plots, and you can see how they are plotted. Only child, first of many, last of many, middle of many. Looks like the middle of many has the highest enjoyment, whereas first and only have the lowest enjoyment. Interesting. Usefulness, again, sort of same. Middle of many find Excel to be the most useful, whereas only child, least useful. And decision quality, middle of many. They perform the best in terms of, they think they find the best decisions or something like that, or make the best decisions. Remember, this is perceptual self-reporting. And only child and first of many have the worst. Now the question is, are these actually significant differences? This ANOVA table here tells us at large across all groups, yeah, there's a significant difference. But I want to know, is there a significant difference between 2 particular groups? So if I were to go to this table, this Bonferroni's pairwise comparisons table, I could see for enjoyment, only child, they're different from last of many. Here's the sig value, the p-value, and from middle of many, but they're not different from first of many. So this tells us for every paired group where the differences actually are. Last of many, they're not different from middle of many, but they're different from most. And same with middle of many, not different from last of many, but they're different from only and first. So you can see exactly where the differences lie. Cool. That's difference of means. If you have a variable and you want to know, is this different across groups? Use a difference of means test. For most treatment control lab experiments, means tests. You want to look at the difference between the control group and the treatment group. Means test. If you're applying a training treatment in your company and you want to see if the training is working, means test. We did this with security behavior. We wanted to see if security training made a difference, and if there was a difference between no training and some training, and also between some training and video training versus human training. It turns out there is a difference. Video training is better than human training. Weird. I don't know. I haven't theorized yet why that is. Okay.
You stop and repeat.
I guess, yeah, you can review and rewind, and maybe it's more engaging than someone droning on up at the front of the room. Could be. Okay. I've never enjoyed that kind of lecture. Okay. Variables moving together. This is, you can test for correlation or regression. It's all about, when the response of a participant is low on one variable, is it also low on another variable, or is it like high on another variable? Do they move in sync, whether that's inversely or together? In this case, as autonomy increases, job satisfaction increases. As autonomy decreases, job satisfaction decreases. They have a very nice in sync correlated set of variants. They might also move like a lot. If autonomy moves a lot and job satisfaction only moves a little, they're still moving together. It's just a weaker relationship. Or they could move inversely, like this, where autonomy decreases, job satisfaction increases. There are cases like that. Or it might be where there's no correlated movement at all. As autonomy increases, job satisfaction decreases for some, but for others it increases. And so there'd be no relationship. This is a fun slide, probably the funnest slide I have for the next 3 days. Setting expectations. So when you record when you capture data from a user, from some participant, you're not just capturing what you think you're capturing. You're capturing multiple aspects. Multiple things go into determining what number is put in that data set. The thing you want to capture, of course, is the trait variance, the true construct that is in that respondent. If I'm asking about autonomy, I'm going to know how they really feel about their autonomy at work. And that's what I think I'm capturing. And that's what I'm theorizing about, right? When I'm making my theories, I'm making my theories about the trait variance. But in addition to the trait variance, I'm also capturing measurement variance and also response variance. Measurement variance, that's the variance that is built into our instrument. So let's say I'm giving you a Likert scale from 1 to 5. And I ask you, to what extent do you feel like you are in control of your schedule at work? And you say, like between a 3 and a 4. But you can't answer between a 3 and a 4. You have to answer 3 or 4. You're like, well, I'm not really a 4, but I'm not really a 3. But you got to pick one. So there's some measurement error. I shouldn't say error. There's measurement variance. Measurement error is a different thing. There's some measurement variance in that response. There's some variance due to the way we measure that is influencing the number being given. There's also response variance, which is due to the respondent's reaction to our question. Let's take those questions about bribery, gossip, and things like that. If I ask somebody, if I put on my survey, I like to gossip a lot, and I give them a Likert scale, strongly disagree to strongly agree. Well, whether the true trait variance that I want to capture is being captured is that it's being influenced a lot by the social desirability of the way we should answer that question. So the reaction the respondent has to that question will push the true trait value away from its trueness. It'll push it down the scale or up the scale. And that's the response variance that's also being captured when we measure anything. So all of these things together is what we end up getting in our data set, even though we're only theorizing about trait variance. Hopefully that was somewhat enlightening.
Very enlightening.
Oh yeah, it's not talked about a lot. We think we're capturing what we intended to capture. We are, hopefully, plus some noise. So there you have it. Let's do a correlation. Here's a fun correlation. Total revenue generated by arcades correlates with computer science doctorates awarded in the US at an R of 98. That is really high. They share 98% of the variance. That is crazy, but maybe rational given the specific variables here. Let's go look at that in SPSS. If we go over here to SPSS, you can do a correlation analysis, which is fine to do if you're interested in bivariate, 2 variables at a time, relationships, not controlling for anything else. You'll see what I mean in a moment. If we were to go to analyze, correlate, bivariate, and analyze, correlate, bivariate. And then let's just go to the bottom again and look at these averages. Let's do these 4. We don't want to do child order because child order, again, is it's nominal. The number that we're correlating with is meaningless. So you don't want to throw something in there that has non-numeric meaning. So, for example, child order, I think a 1 is first of, only child, 2 is first of many, 3 is middle of many, and 4 is last or something like that. Those numbers are meaningless in terms of correlating their variance. So don't use those. I'll just use the defaults here, hit OK. And here's our output. Zoom in here. We can see that enjoyment correlates with usefulness with an R of 0.47. If you were to square that, you get the R squared, which is the percent of shared variance. So in this case, 0.47 times 0.47 is what, 0.17 ish. So they share about 17% of their variance, something like that. And is it significant? Yeah, in this case, the 2 stars here indicates that it is significant at the 0.01 level. Being an early adopter of technology correlates with enjoyment of that technology. Same with usefulness, decision quality. So that's correlation. What we're not accounting for here is the dual influence of other variables. If I were to throw another variable in here, into this correlation analysis, none of these numbers would change 1 decimal point, even out to 200 decimal points. The R is unchanged because every variable I add or take away has no influence on the correlation between other 2 variables in a correlation analysis. Whereas in regression, I add a variable, I take away a variable, everything changes because it's all accounting for the explained variance of the other variables. So if you want to control for the effects of other variables, don't do a correlation, do a regression. Okay. Any questions about that? Correlations are bivariate. They ignore all other effects. Regressions are multivariate. They account for the effects of all of the variables in the model. Regression. This is the only formula I have in all of my slides. It's fairly basic. You know this one, hopefully. It's the same as you learned in high school, y equals mx plus b, or y equals a, b plus x, or there are various ways of m, I think. Anyway, but y is the thing we want to predict. The beta naught is the intercept on the y-axis. The beta 1 is the slope, the actual regression coefficient, unstandardized. And then x is the observed data point, and then there's some error. Anytime you're predicting anything, there is error. So if we had our dependent variable of job satisfaction measured low to high, 1 to 5, and autonomy, same as our predicting variable, our independent variable, we could have something like this, where again, autonomy on the x-axis, job satisfaction on the y-axis. Here's everybody's response. Here's Bob's response. Bob said, I don't have a lot of autonomy and I don't have a lot of job satisfaction. Just kind of me. Whereas Pat, tons of autonomy, tons of job satisfaction. Tom's a weird one. Tom has very little autonomy but loves his job. And Dave's a little weird, has a lot of autonomy but doesn't really like his job. So that's how you would read this. The distance from this line of optimal fit, the line of least error, the regression line, many different names for it. The distance any point has from that line is its error. It's the distance from what we would expect, the different distance from the predicted value. So that's where error comes from. Anytime you're predicting, there's error, and the error is the distance, roughly speaking. So that's regression. It's not that complicated, I think. You know. And the slope you learned before, it's just the rise over run, right? It's the angle of that line. Oh, good. It's not that complicated, really. Yeah. And this line is generated by minimizing error. It's the line of least error. So wherever that line could be, so that when positioned, if it were to move in any way at all, it would increase error. That's where that line's going to fit, is where it's minimizing error. Squared. Well, yeah, the distance here squared is that error. Anyway, so that's how that's created. Yeah.
James, so is this the same structural equation as structural equation model?
Yes.
So it's basically the same.
So to some extent, there are other advanced algorithms that go into it, like maximum likelihood and GLM and things like that, and Bayesian estimation, which are built off of this, but they have additional parameters. But you need to understand regression to understand the output of an SEM analysis.
Wow.
Make sense now? Good. Yeah. Okay. Confidence in findings. You should probably all see this as a review. The confidence is just the degree to which you believe that your effect is different from zero. So if we had this scale here and we said that the predicted value, not the predicted value, the regression coefficient, the beta up here, B1, is different from zero, and we're 99% confident, p-value of 0.01, what we're really saying is that regression coefficient and its 99% confidence interval doesn't contain the value 0. In this case, we'd be wrong. 99% confidence interval from -0.5 to +4 does contain 0. Therefore, we cannot be 99% confident that the estimate is different from 0. But we can be 95% confident that that estimate is different from 0. So if your confidence intervals contain 0, then you cannot be confident, that confident at least, that the estimate isn't 0. Because 0 is in that confidence interval. But if 0 is outside your confidence interval, you can be that confident that your estimate is not 0. Meaning there is an effect. The null hypothesis is rejected. So that's confidence. In social sciences, we use 95% most of the time, but that's not consistent across all fields. Even in social sciences, I've published stuff at 90% confidence. I've seen 80 even in truly exploratory stuff. In physics, it's the 5 sigma. In fact, when they were doing the Higgs boson, when they were trying to determine with confidence that their tests were truly detecting a Higgs boson, they were not confident until they could say with 99.999999% certainty that 0 was not within their confidence band. Which means these bands would have to be super wide and not capture 0. So they want to be sure. Okay. P-value is just the 1 minus the confidence level. This gets back to one of the questions asked earlier. Some journals have banned the reporting of p-values because you can just p-hack, right? You can, I think maybe it's one of these next slides coming up, you can just increase your sample size to reduce your error, to increase your critical values to reduce your p-values. You can totally p-hack it. Or increase the number of variables you're assessing simultaneously, and then something's going to be significant, right? And so some journals are banning the reporting of p-values because they're meaningless, because you can manipulate them. And so what they require instead is effect sizes, which we'll talk about Saturday. Effect sizes, R-squares, and other things like that. You can do random sampling, smaller sampling, and then report p-values. some journals are requiring multi-sample. That's what I was getting at with the previous question. You have to show the robustness of your effects over multiple samples or collect qualitative data to augment and confirm your quantitative data. And that's considered the most rigorous approach. Okay. What do I want to say about this? When you're testing hypothesis and regression, you got to look at a lot of things. In fact, here's a slide I made about all the things you need to test when you're assessing a regression. The very second to last thing you test is p-value out of like 38 things that you need to test when assessing a regression. It's only at the very end that you can have confidence in that p-value. And then it starts to make sense, space validity. So, but what we typically look at, assuming we've done all of our homework, all this stuff before, then we look at the R-square. Is it sufficient? R-square is the amount of variance explained in that dependent variable by all of its predictors. So in this case, what percent of monthly sales can be explained by salesperson attractiveness and their confidence? Turns out it's about 42% of their sales performance. And is that a big enough number? If it isn't, then we don't even care about the regression coefficients or the p-values. They're meaningless. If it's a big enough number, then yeah, let's go look at the regression coefficients and see if they are significant and meaningful. Yeah.
But in terms of that being enough, it just depends on.
Depends on the field. Yeah, what is enough in an R-square? In social sciences, typically we like to see above 0.2 as a minimum. Although I've seen stuff published at 0.1. Anything less than 0.1, like if you want to predict job satisfaction, very social science kind of thing, and you can predict like 5% change in job satisfaction. It's not like a lot. 40%, that'd be great. In finance, quite different. In finance, if you can predict 2% of sales change, like change in revenue, I would love to know your formula. That'd be great. So R-squares in finance are quite a bit lower. In medicine, it's quite a bit higher. You want to be able to, well, depending on the design of your study, you want to be able to rule out all side effects, right? And other confounding variables. So it just depends on your field. Any other questions about regression? Okay, we're going to get into it. Let's do a regression. Oh, here's another slide I made a while ago. P-value is only meaningful if there's an effect, which is only meaningful if the R-square is big enough, which is only meaningful if you have model fit, which we haven't talked about, which we will later tomorrow, and then other stuff. Data validity we looked at today, normality, outliers. If you've taken care of that, then other stuff makes sense and is meaningful. Sort of like here, you got to take care of your data screening first. Otherwise, your EFA, factor analysis, is going to be meaningless, which means your confirmatory factor analysis will be meaningless, which means your causal model will be meaningless. You got to do things in order by stage, or else you're undermining all of your results. In fact, I had an email today. Somebody said, my beta, my regression weight is above 1. What do I do? I'm like, well, I wanted to send him the slide. Did you do all this? Because if you didn't, it could be in any of those. The error could have been in any of those little steps that you missed. I simplified it, but you won't run into as many issues down there where you're testing your hypothesis if you've done all the stuff before it. And we are going to do almost all the stuff before it in this workshop. Okay. Okay. Are we talking about this? I just zipped past it. Did I? Yeah. I just zipped through it. But the idea is with regression-based statistics like SEM, you can always decrease error by increasing sample size. Due to the central tendency, people tend to answer in populations towards some sort of central tendency. And so as you get more data, there's more sample for less error. If that makes sense. It's like when I go over here and I add another data point, most data points are going to be around this line. Some will be out here, very few, but most will be around this line. So the more I add, the less the error from this one point actually makes a difference because it's being absorbed and minimized by all the other points. Yeah.
Right, so the example has the person's age.
Yeah,
in that.
probably no effect since we have 380 people. Yeah, but if I only had 8 people, yeah, that would be a huge effect, huge error. So I can decrease the error by adding people or responses. And as you decrease error, the actual calculation for significance for a critical value is just the estimate divided by its error. And so the lower the error, the higher the critical value. And the higher the critical value, by definition, like the mathematical proof for it is the p-value drops. The higher your critical value, the lower your p-value. So it's good to understand that. Also good that, so you won't manipulate it. And so that when you do a study, I just did a study with 5,600 something African entrepreneurs, Nigeria and a few other countries. And all of our p-values were significant, obviously, because we had 5,000 responses. So the error was nothing, which means the critical values were enormous. I had critical values in the hundreds, which is big. Anything above 1.96 is considered significant at 95% confidence. And so our p-values, of course, were just nominal, just so small. But back to here, was the effect big? Was it in the right direction? Was the R-square meaningful? All of those were more important in this study because we have the sample size. Was there a question?
Yeah.
No, we're good? Okay. Okay. This is awesome. We finished 27 minutes early, which is good. So let's do this. We can either do some exercises if you want to reinforce this with yourself, or you can do it during lunch. You're welcome to do that during lunch to reinforce some of these skills. Or we can check out a couple of these things, like how to do random sampling in SPSS, or how to do automatic linear regression for predictive analytics in SPSS. That's a fun one. It's super easy. It'll take like 2 minutes to show you. How to do all this stuff in Excel if you're not using SPSS, but I think most of you probably have SPSS. Do any of these stand out to you? How do you do categorical? We didn't even do a regression. We need to do a regression. I'm sorry. Let's do a regression in SPSS. Then we'll get to this stuff. Okay. Here we go. In SPSS, let's do this. Let's go to Analyze, Regression. Whoop. Regression, linear. You may notice there are lots of different types of regression. I am only going to cover linear in this class. Unless we do automatic linear, then I'll cover that. But all the rest, or I might cover logistic as well if you want to hear about that. Linear is mostly what you use for normally distributed, numerically meaningful variables like ordinal and continuous variables.
Even though we had slightly tested some of this data, we still
Normal enough.
So
Unless I was trying to predict education, which was super church out, I'm not too worried. Logistic regression is when you have a dependent variable that is categorical. Did I get that right? Yeah. Let's say we're trying to predict child order or something like that, or predict what type of customer you are, or predict what type of car you're going to buy. We have different categories. We could predict that using logistic regression. All right, but let's do linear. And let's just go down to the very bottom. And let's try to predict decision quality as our dependent variable. And let's use experience, frequency. I'm just holding control and clicking. Enjoyment. Let's throw those 3 in there as independent variables, the things doing the predicting. There are a bunch of different things we could do. You can see all these buttons on the right. We're not going to click any of them. Just stick with the basics for now. Hit OK. This will produce this table down here. I should explain all these tables. Let me zoom in. Okay, the model summary table is the R and R square. The R is literally just the correlation value. The R square is the amount of variance explained in the dependent variable by these 3 independent variables. we can explain 21% of the variance in decision quality with these 3 variables. So that's good. It's not fabulous. It's good. It's good enough. The ANOVA table, which is confusing because there's also the ANOVA difference of means test. Don't think of it this way. There's a different thing. This says, to what extent is this model good? Is this model better at predicting or not better at predicting? The p-value here says, yeah, these 3 things together predict decision quality pretty well. Then the coefficients table is where you'll be looking at the most. This says for each variable, what is the effect and its significance. Also, it's controlling for the effects of all other variables. So you'll see in a minute, we'll throw in another variable. It's going to change all of these estimates. There's the beta, the unstandardized beta. This is the literal slope of the regression line. The standardized beta, this is, if you were to, it's the relative effect between -1 and +1. Let's look at it that way. It's not the exact slope. It's just the relative effect. So a bigger means more effect, either in the negative or positive direction. A negative effect in this case would mean as that variable goes up, decision quality goes down. T-statistic, this is that critical value I was talking about. Anything over about 1.96 is considered significant at 95% confidence. And then the sig or p-value here is the p-value. So it looks like experience has no effect different from 0. At least we're not confident that there's any effect different from nothing. Frequency has a pretty good effect, or at least we're confident in its effect, and same with enjoyment. But watch if we add, let's run this test one more time, linear regression, and let's add usefulness as a predictor. Hit OK. These estimates are going to change, probably. Experience, still no significant effect, but look at this, frequency, no longer significant effect. We're no longer confident in its effect. Enjoyment still has an effect, and usefulness has a very strong 0.411 standardized effect. The R-square probably increased, yep, 33%. So notice regression accounts for all other explained variance in the model. So the effect of frequency changed quite a bit when we added usefulness. Whatever variance in decision quality was being explained by frequency was actually being explained by usefulness. So it sort of drew that variance explanation away. Okay, that's regression. And that's what most of SEM is built on.
So typically when you report regression results, you report the unstandardized beta coefficient? So
I typically report the standardized coefficient. So the unstandardized coefficient, it's the literal slope. But the problem with it is it is...
you would interpret the unstandardized as a 1 unit increase in
exactly
enjoyment
leads to a
0.17
exactly change in decision quality. So you have a literal interpretation here with unstandardized. But in terms of relative impact, it's hard to judge because the size of the unstandardized effect depends entirely on the size of the scale. So we use 1 to 5 scales for all of them, so they're actually all relative to each other already. But let's say we threw in age or income or something that wasn't on a 1 to 5 scale. Then these numbers, let me just show you. If I throw age in here, let's see, age, there we go. Throw that in there. You can see the size of age's effect is ridiculously small because 1 unit increase in age is a whole year. And so that had a whole year difference makes 0.002 change in my 1 to 5 scale decision quality. It's the same when you throw income in there, then you start having hundreds of thousands in the number scale. And then those unstandardized coefficients get infinitesimally, just asymptotically, is that the word? Small? I think that's the word mathematically. But the standardized coefficient will still be relative to the others.
So the interpretation then becomes a one standard deviation change in
Yes.
usefulness leads to a 1 unit change in.
Leads to a, yeah, it's a standard deviation change interpretation instead of a unit change interpretation. Yeah. We usually report the standardized regression coefficients. That's the short answer, but yes. Okay. Okay.
So
Yes.
when you're running your regression, how do you choose the variables to include, since every time you include or remove one?
Oh, this is a good question. I have a slide on this. The question for the remote folks who couldn't hear, the question is, well, if everything changes when you add or remove a variable, how can we have any confidence in our findings, and which variables should we be including or not including? That comes over here to nomological completeness, which means, is your model accounting for all things that it should be accounting for? I did a study on firm performance several years ago, and we found that the way you decide on the way you price your products, whether you do value-based pricing or competitor pricing, matching, things like that, or cost-based pricing, makes a huge difference in your firm performance year over year. And the reviewers sent it back and said, no, it doesn't. What about firm size? Firm size predicts firm performance. And we didn't account for firm size. And so we threw firm size in there. We actually captured it, but we didn't include it in our model. We threw firm size into our regression, and sure enough, there was no effect from value-based pricing or cost-based pricing. It was all about firm size. And so we were nomologically incomplete until we added that variable. And so what you have to do is you have to know the literature around that theory you're trying to forward, and you have to know what other people have said predicts that dependent variable, and you have to account for those potential confounds, or else somebody will come back and say, no, I have no confidence in your findings because you're not accounting for firm size or whatever it is that really is the lurking predictor. Yeah. But I have seen also, you have a model, you run it, p-values aren't significant, remove a variable, p-values are significant. Ah, this is my theory. That's not right. That would be a little unethical. Yeah. Okay. Speaking of unethical, I want to show you how to do automatic linear modeling in SPSS. If you go to Analyze, Regression, Automatic Linear, there's actually quite a different school of thought in data analytics versus academic research. Academic research, you theorize, you say, this is how I believe the world exists. You collect data on that theory, you test that theory, and then you say, ah, I was wrong, or ah, I was partly right. And whereas in the field of data analytics and data mining, it's here are all our variables, let's see what predicts what. What is the biggest relationship we're not seeing by theorizing? So it's the other way around. You data first, then theorize why those relationships exist. Whereas we typically in academia, theory first, then use data to support or project that theory. Okay, automatic linear modeling is the analytics approach. Let's say we want to predict. Let's go down here to decision quality. We want to predict decision quality. So we throw it over here and then throw it up here. It's kind of weird. It has to like loop around. And then we say, out of all of our predictors, let's push all these over here. Okay. What of these do we want to use to predict? And so we're going to go down at the bottom, get all those ones that are averages. I want to use, and you can even use categorical in this, which is kind of cool. So I'm going to use comp score all the way down to early adopter. I'm going to use all those as predictors. And then I'm going to just run it. It's going to think for a bit, because what it's doing is it's trying to find the best possible fit and the best possible prediction. And it comes up with this, which if you double click, gives you a few things. The first thing is, it says if this is a good model. Can we predict decision quality? The answer is, yeah, sort of, 35% adjusted R-square. And we can scroll down, next window, it says, here's what I had to do to get the model to work. For each of these variables, I had to trim outliers, merge categories, and it also transformed a few. So this is what it had to do automatically for me. And then it says, now out of all those variables, usefulness is definitely the best predictor of decision quality. Next would be enjoyment, then average of adopt. Whether you're an early adopter or a late adopter of technology, and whether you are a comprehensive user or a non-comprehensive user of Excel. Skip that one, skip that one, skip that one. Here we go. This one gives you a more visual target. It even puts a target on here, just in case you're confused with what we were doing. And it says, look, usefulness is the biggest predictor. Its significance, 0.000. And then enjoyment. And then that one, and so on. And you see the p-values on these. And so you could, if you had no idea what predicted your dependent variable, throw all your variables in there and let it decide. It decide what the model is. And now I would say, oh, well, let me go create a model where I have these 4 variables as predictors, and then here's my dependent variable. This is pretty atheoretical. It's not encouraged in social sciences, but it is an approach you can use if you're completely stuck. Then you need to re-theorize. Let's say my whole theory was out the window. What I'd have to do at this point is say, oh, usefulness, never thought of that. Why does that make sense? And I have to go figure out a theory for why that made sense. Because without a theory, it's just statistical anomaly.
So if academic research is interested in advancing understanding and knowledge, why wouldn't this also be a useful tool to say?
For the remote folks who couldn't hear that, we have a skeptic in the room. No, devil's advocate. Or just the devil himself. The question is, if the purpose of science is to advance knowledge and science, why not use this approach? It reveals the greatest predictors. Why wouldn't we want this approach? And the answer is because we're old and we move slow. The way we've done it in the past is we haven't had the computer resources to run models like this. And so the fastest, optimal way to test a theory would be to theorize first. And then only collect data on your theory, because collecting data is hard. And then only analyze what you theorize about, because analysis is long and hard and takes forever. And so it's path dependence. This is what we've done for 350 years. So we're going to keep on doing it. Yeah. Is there value in this approach, though? Yes. Yeah, I'm learning, all the best ways to model my data. Now, there are ways we've accommodated this in academia through tests of model fit, which we'll talk about probably tomorrow. Talk about model fit, and that will account for. It'll make sure we don't miss big relationships that we didn't theorize.
James, is there a plug-in that will actually write the paper and do the lit review based on what it finds?
I have been asked multiple times to write a plug-in that would just write the paper for them. I've been sorely tempted to write a plug-in that would automate the methods section. All you have to do is fill out a few forms for me, and I will just write the methods section with the plug-in. Because it's all the same. It's like, we found this, and we found that citation, this citation, that. Here's the threshold, we met that. And in fact, I've been called out before in submitting a paper. It got rejected, desk rejected by the system because it said it's plagiarism because my methods section was identical to another methods section that I had written because they were identical. I mean, except the numbers. I changed the numbers, but the wording, it's all the same. The citations are all the same. I got rejected for that. But yeah, it's all the same stuff the way we write it. But no, I have not. I've decided not to. I've been discouraged from doing it from other scientists. Students would love it though. Yeah. Okay. We did automatic linear regression. We have 20 minutes. Control variable. Another option is I can just work with you one-on-one. That might be. I do want to show you, actually, I do want to show you this because people get this wrong all the time. Control variables. or categorical variables in regression. I want to show you this. So like if in automatic linear modeling, we can throw child order in there, no problem. It just handles it, knows what to do. But if we're doing SEM or a regression in SPSS, we cannot just throw child order in there because the order number doesn't have any meaning. And so what we'd have to do is recode it as this. Let me show you. I'd have to have a first of many, let me zoom in, binary variable, and then a middle of many variable, and then a last and an only. And each of these would represent, if the value in this variable had a 1, it means yes, true, present. I'm the first of many. And then all the rest would be zeros. If I were the middle of many, I'd get a 1 there, but I'd have a 0 on first, last, and only. And then you can include those binary variables. They're called dummy variables. I'm not sure why they're called dummy variables. Does anyone know? Okay. I should have made something up then. But you can include those binary variables in your regression, except one. You have to exclude one category as what's called the reference category. Otherwise, you've locked yourself because there's no escape if you have all possible values covered in a set of dummy variables. So you have to exclude one of those dummies as your reference category, and then the way you interpret the statistics is difference from the reference. That probably didn't make sense. Yeah, go ahead.
So in this example, you would take out like only.
Yeah, take out only child, and then all
all
the estimates. Let's say the regression weight is 0.5 or something like that. That's 0.5 relative to only.
Right.
Yeah.
Yes.
It's the reference category.
Because I couldn't be an only child in the first.
Exactly. So I'm different from the only child. I am this coefficient.
Like a Venn diagram.
Yes.
Right.
To some extent. Yes. So the reference category is the relative. It's the thing we reference in looking at interpreting our estimates. So that's how you do dummies. There's actually a way to do this automatically let me delete these, in SPSS. Don't follow along, but I just want to show you. If you were to go to transform and automatic recode, create dummy variables. I'm gonna do that one. Create dummy variables, and I stick in child order, and make sure I have all these settings right, and then, yep, and then, nope, I don't want that. And then the root name, it's going to be child order. And then it's going to do child order 1, child order 2, or something like that. If I hit OK, it's going to automatically detect my categories. And then it's going to create the dummies. And it will produce them right here for me. I'll show you. So child order 1, 2, 3, 4. And it says this is the only child, first child, last child, middle child. And then you can see, if I click on them, you can see over here, this first person was, let's zoom over here. This first person was child order 2. They were, whatever that is, middle of many or something like that. They were not child order 1 or 3 or 4. So those will be zeros. There'll only be one in that set of 4 variables. The rest will be zeros. Cool. And then if I want to use the prediction, I would go like this. Linear regression, and I'd throw in those dummies except one of them. So let's not throw in, I can see their labels. Let's see, let's not throw in only child. We'll throw in the other 3. And so now only child is our reference category. I hit OK, and we can look at the estimates. And these regression coefficients here are relative to the only child. So in all cases, being not an only child is better, and it leads to more decision quality than being an only child, because these are all positive. If any of them were negative, then I'd say, oh, being an only child leads to more decision quality than being whatever child that was, because it's relative to that reference category. Woo! Okay, we have 2 questions on chat. Collinearity between variables. Can you say something about this? Heck yes, I can say something about this. Collinearity. Let's go ahead and do this. Let's run the same regression. And change that back to names. If you look at statistics, collinearity diagnostics. Again, that was in the statistics button right here. Check the box for collinearity diagnostics. I'm going to show you what it does, but then I'm going to tell you what it is. Hit continue, and just hit OK again. And what this will do is it will produce a new table for you, collinearity diagnostics. And coefficients, that's actually the one I'm going to look at. In the coefficients table, there are 2 new columns, tolerance and VIF. VIF is the variance inflation factor, which means to what extent are 2 or more variables explaining the same variance in the dependent variable, thereby inflating the R squared. And so you don't want that. You don't want 2 variables explaining the same variance, identical variance. And the extent to which they do, it jumps up the VIF, so higher VIF is bad. What is the threshold? It is, well, depends on who you look at. It's 3, 5, or 10. 10 is like really extreme. 5 is usually my cutoff. In this case, this one, the last one, has the highest one, which is child order. So child order, I would expect the dummy variables to do some overlapping variance explanation because they're from the same variable. In fact, I'm surprised they aren't higher than this. That is very surprising. Yes?
Explain the tolerance there beside the bit.
Yeah, so tolerance is just the inverse of the VIF. So you see as VIF increases, tolerance decreases. Any tolerance less than 0.1 is considered really low. So we're good. But if it got down to 0.1, yeah, we'd be in trouble. That's that. Yeah.
I'm not sure I understand the relationship between VI, well, so between collinearity and when I have reflective items forming a construct.
Thank you.
They're also related.
Yes. Okay, so the question for the remote folks who couldn't hear, what is collinearity in a measurement model where items predict or are predicted by a latent factor, which we haven't even gotten to yet, that'll be later today, and in a structural model where you have constructs predicting each other. What I'm talking about here is constructs predicting each other in the structural model. And that's where we look at VIFs. In a measurement model, in a reflective measurement model, we don't look at VIFs. We do in a formative one, which we may get to on Saturday. But most of what you guys will be doing, you don't look at VIFs or collinearity except in a structural model where you have variables predicting other variables. If you do, let's pretend for a moment we did have a VIF that was super high, like over 5 or over 10, that variable is useless to us because it's completely redundant with some other variable because it's explaining the same exact variance. In fact, if we were to remove that variable, the R square would change by almost nothing because it's explaining the same variance. So we could just remove it, which is hard to do. You never want to remove a variable, but there are times. Okay.
James, can you hear me?
Yes, I can hear you.
What if my dependent variable and the mediator in the SEM model are extremely, like, highly correlated? The R there is like above 0.6. Would you suspect then that it's collinear? And how would I get rid of it? Or the whole model.
If what value is above 0.6?
The arrow between the mediator and the dependent variable.
Oh, if the arrow is?
Yes.
Like, yeah. If the regression coefficient is above 0.6?
Yes.
That's fine. We start getting really suspicious if it's above 0.8. Then we think there's a tautological issue. So tautology is when you have a variable predicting itself, which you don't want to do, obviously, because then you just inflate the R-square artificially. So in regression, anything over 0.8 is truly suspicious. We might start getting suspicious above 0.7. Anything less than 0.7, I'm not too worried about. Is there a citation for that? Maybe. I'm really bad with references. Google it or use Haradol. He doesn't mind. He's retiring. He would love for you to cite him. Joseph Hare. If you guys want references, by the way, which I'm terrible at, this is my true weakness, is references. I have a whole section of the StatWiki devoted to references. So in this case, general topics, here's the Hare book right here, Joseph Hare. But there are many references for many different things. Okay. Any other questions before we break for lunch? We do have some on remote, let's see. All right. Naveen, you have questions related to correlation, Pearson correlation?
Yeah, the collinearity that I was asking about right now with the SIM model with the arrow above 6, I ran a correlation of Pearson and there I saw the above 6 numbers.
Yeah, whereas in the regression it'll be different. Because the regression is accounting for all the explained variance of the other predictors, whereas the correlation, the Pearson's correlation, doesn't account for those other explanatory variables. So we can handle correlations up to 0.8 as well. Anything above 0.8, and then it's like, those are the same variable.
So you would not recommend to get rid of it?
If it was above 0.8, I'd say, well, it's probably redundant. Or it's another dimension of the same factor, of the same construct.
Right.
Let's see, Lori says the tolerance column is decimal number, so they are all below 1. Yeah, tolerance is going to be less than 1, and if you hit 0.1, less than 0.1, then you're in trouble with the tolerance column. Although VIF is just as fine. Tolerance and VIF are just inverse of each other. So you can use one or the other. You don't need both. Okay. Any other questions before we break for lunch? All right,
Great job.
It's exhausting. Yeah, thank you. All right, I'm going to stop recording. Remote folks, I'm going to post this on YouTube either during lunch or after lunch. We'll see, or after the afternoon, and then I'll jump back on here about 10 minutes to before we start up. We'll start up in 2 hours. So we're good to go. Have a great lunch, or wherever you are in the world. I guess we have some from Europe, some from the UAE. We have some from the US, some from Mexico. Yeah, cool. Take care.
So James, you didn't talk about stepwise regression.
I didn't talk about stepwise. Let me stop recording for a sec here.